I hate being saddled with a boring name. What I could do with is something a bit more muscular. Now that's more like it. Or perhaps something mysterious. Welcome to the Particle System Part 10. It's been a long time. Sorry about that. But it's time to get back in the saddle and explore some more of MODO's particle features. And now we have a new version of MODO to play with. In this video, I will look at making particles interact with one another. Normally, each particle in a simulation is completely oblivious of its siblings. It's as if they didn't exist. Here is a strained analogy which is of no help whatsoever, but I just like it. So usually, particles behave like bosons. The quantum of light, the photon, is a boson. You can pack as many bosons into a space as you like. They just don't mind. Boson-like particles are good at simulating gases, vapors, and smokes, where each particle can be considered in isolation. But they are no good when it comes to fluids. The other class of fundamental particle is the fermion. Fermions make up the stuff of the universe. Fermions don't like getting too close to one another. They like their own space. It's because of this that substances have bulk. If we are to simulate fluids, then we will need a bit of fermion action. But before I get into any of that, let's look at some of the nice additions to the schematic editor that arrived with 801. Here we are back in the good old Setup tab, ready to use the schematic editor. One of the standout improvements in 801 is the ability to connect vectors without having to connect the individual components. So if I'm wiring the output of this matrix vector node to the vector A input of the add node, I can do that with a single connection. If you need to go down to the individual components, then just click on the arrow and you can open them up and interact with them individually. This is a great time saver. You have to do a third of the work when dealing with vectors. Next up is a great feature for making multiple connections. If I want to connect the output of each of these three nodes to this input, I can select using Shift and then just drag from one of the connection points and make the connection. Similarly, if I want to connect this output to all of these inputs, I can select the inputs using Shift and drag and connect. Let me show you this wonderful workflow for connecting multiple prototypes to a replicator node. If I select the items that I wish to connect as prototypes, drag them into the schematic, and then Shift, click and drag, I can connect all of the items in one fell swoop. How cool is that? Here's another cool thing. If we want to add channels to nodes, then in the bad old days we had to select the node, rootle around in the channels list, select the things we wanted to add and drag them into the schematic. Well, now in 801 there's a quicker way. We just right click on the node itself, go to Add Channel and find the channel that we want to add. Much quicker. Finally, there's an auto zoom facility in the schematic. When schematics get big and complicated and we have to zoom out, then it can be difficult to see the detail. But if you hover over a node, it will automatically zoom to full size so that you can see the channels and make your connections as required. Okay, enough schematic wizardry. There are bound to be lots of other features that I've forgotten, but they'll have to wait for another video. I know that what you're really interested in is interacting particles. I'd like to introduce you to SPOC, Steve's Particle Observatory and Collider. I'm going to use this to demonstrate some of the ways that particles can interact with one another. SPOC is a fairly simple setup. I've got two vertices in this emitters object, And they're the things that are connected to our source emitter, which in turn is connected to the particle simulation. So we'd expect these emitters to emit particles. Normally they'd emit particles in all directions at once, but I've set up this very simple rig to make sure that they are emitted along the Z-axis. So what happens is that I take the position in Z, which is either going to be in the negative direction or the positive direction. I use that, scale it by the initial velocity, and bung that into the Z velocity of the particle. So what we should end up with is particles shooting along the Z-axis. Now for the experiments, I don't want to have loads of particles spraying off. I just want a short burst of a limited number of particles. So I've animated the emission pulse channel. If we look at it in the graph editor, then we can see that we've got 4 pulses, so we should get 4 particles emitted in the first 8 frames, and then on there's no more pulses. If you remember from some of the earlier videos, if we set the emit mode to pulse, it will emit particles just when this pulse channel is asserted. So let's just run it and see what happens. There we go, 4 particles emitted along the Z-axis. And because these are bosons, that is, there's no particle interaction going on, they just carry on past one another as if they're not there. To make the particles interact, we essentially have 3 options. We can use the flocking operator, the dynamic fluid operator, or new to MODO801, we have the dynamic replicator. Let's start with the flocking operator. Here's one I prepared earlier. I'll connect it into the particle simulation and run the simulation. You can see now that the particles are interacting with one another and they're tending to clump together. The various settings here control the precise nature of the clumping effect. The minimum distance controls how close the particles are allowed to get. The maximum distance controls how far the attractive force between particles will reach. If the particles are very far apart, that is further apart than the maximum distance, then they won't affect one another. The number of neighbours controls how many particles are considered when computing the forces on each particle. It effectively controls how clumpy the effect is. Beware that high values mean a lot more computation. The remaining controls affect how strong the various forces between the particles are. Cohesion is the attractive force that tries to bring particles together, and separation is the force that keeps them apart when they get too close. Alignment is slightly more subtle in that it tries to get the particles in a group to have the same velocity. In many circumstances, like modelling a curtain of water, the particle flocking operator can be quite the dab. In this example, I have a curve feeding into a curve emitter, which is producing this waterfall effect. Without the particle flocking operator, the effect is, well, boring really. But let's connect in the flocking operator. Well, the immediate effect is that it slows down the simulation, but you can notice now that the particles are beginning to clump together in the way that water might be expected to. I can fiddle around with the settings in the particle flocking operator to see how they affect it. Let's reduce the number of neighbours to say 5. You can see that the graininess of the clumps is affected by the number of neighbours. If we increase it to 20, we should get rather less dense clumps. Put it back to 10. What happens if I increase the cohesion force? Let's put it up to 300%. Oh look, the clumps are much more tightly bound now. So you can see you can fiddle around with these numbers to your heart's content until you get the sort of effect that you're looking for. The flocking operator is, however, not very good for creating bulk. Essentially, it is simulating a fluid with no viscosity. Notice how in this simulation the particles fall onto the surface and they respect each other's space, so they spread out onto the plane. But if we look at this edge on, we'll see that this really has no thickness, it's just the thickness of the particles themselves. So this is a very, very runny fluid. In order to simulate something with some viscosity, we need to turn to the dynamic fluid operator. Beaming down Spock. The dynamic fluid operator is a more accurate simulation of fluids, but bear in mind that it is still relatively simple. It won't be able to compete with dedicated fluid simulation packages like RealFlow, for example.
Other fluid simulations are available.
It can also be quite tricky to get the settings right for the behavior that you're after. The first thing to note with the dynamic fluid operator is that it usually requires a large number of steps per frame. By default, the particle simulation comes in with 1 step per frame. I found that setting this to 10 is not unreasonable when using dynamic fluids. The other thing to notice about this is that when we run using the standard green arrow play buttons, that won't take the number of steps into account. These are for quick previews, and so they don't do a large number of steps per frame. In order to get the result that you're looking for, we will need to bake the simulation. So here are some dynamic fluids that I've prepared earlier with settings appropriate to my scene, and I'll wire one of them up. Let's bake that simulation. Go back to the first frame and play and see what happens. Whoa, that's fun. How about another one with a slightly different set of parameters? Bake the simulation and play. Well, that's even more interesting perhaps. And I have one that's somewhere in between. Wire that in, bake the simulation, and play. This one has a rather tighter orbit. Dynamic fluids can be a little explosive at times. Let's see how this simulation works. Oh dear, it's all gone horribly wrong. The problem here is that the particles are all being created at the same point, and so they're very close to one another, which causes a lot of repulsive forces, and we don't want repulsive forces, clearly. The solution is to create the particles somewhat spread out. So in this case I've created another radial emitter. And rather than just having a point emission, I've increased the start radius so that the particles won't be all created on top of one another. So hopefully, if we simulate this one, we'll get a rather better result. Well, you know that we will, because I prepared it earlier to make sure it works. You know my games by now. So this one needs a bit of me blathering in the background because the simulation is going to take a long time. or I could just skip forward. Okay, I'll do that. Well, nearly there, nearly there, nearly there, and we've finished. Let's play the simulation. It's much more civilized. It's like a dripping tap. Excellent. Here I've used the dynamic system with the particle system and a dynamic fluid to simulate a gloopy goo falling onto a flat surface. This is quite a heavy scene, and we don't want to be running the simulation too many times, so it's worth caching the results. So let's abort. See what we've got so far. This is our gloopy fluid falling onto the surface and bouncing quite nicely. What we want to do is cache the results of this simulation, and MODO801 has a new mechanism for that. If we add into the scene a CSV point cache, this is very similar to the real flow point cache that we had in 701, except that the files are in CSV format, that's comma separated value format, which is something you can read either in a text editor or more conveniently in something like a spreadsheet program. So let's connect up the point cache to our simulation, and now when we do the simulation the data will be saved to our point cache. First we need to create a new sequence, give it a folder to store the results in. Let's call it demo, and give it a file name. I'll call it demo as well. And now when we run the simulation, the data will be stored into that folder with one CSV file per frame. Off we go. Well, I'm not going to wait for that. I'll just get rid of that and show you one that I prepared earlier. I keep saying that, sorry. So actually I've already run this before. Let's browse for the one that I did earlier. And we'll use that for our point source. And this is the cached version. And now we don't need to run the simulation anymore. One thing that I've done in this simulation is I've done collisions with what I've called the collision plane, which is actually bigger than the plane that I'm going to use for rendering. So if I get rid of the collision plane and leave in place the render plane, I'll show you why I've done that. If we turn on the collision plane, you'll see that the fluid sort of joins more or less at right angles to the surface, which doesn't really look very natural. So let's get rid of the collision plane and use the smaller render plane which lies within the collision plane, and now we've got a sort of meniscus type effect where the blobs join the surface. One of the advantages of having a CSV format for our files is that we can view the data in external tools, and indeed if you're up to the task you can write tools to edit the data or process the data according to your requirements. So this is what the files look like. Simply a bunch of different properties like the particle ID, the particle position in X, Y and Z, its velocity in X, Y and Z, and the particle ages and so on, all the things that are generated during running the particle simulation. Right, as a final observation, you'll probably notice I haven't said an awful lot about these parameters of the dynamic fluid. To be perfectly honest, my approach tends to be fairly trial and error, so I'll fiddle around with the numbers until I get something that is more or less what I'm looking for. The radius is quite a critical setting, and also the stiffness can affect the behavior quite dramatically. But I usually just fiddle around until I get something that works for me. You can look in the MODO documentation to see what each of these properties is responsible for, but I'm not sure that it terribly helps in achieving a particular effect. The final thing to look at is dynamic replicators. These allow us to treat particles as though they are genuine bits of geometry, so they can interact with one another as well as with the geometry in the scene. Dynamic replicators are cunningly hidden in the Other section of the Add Item menu. So let's add a dynamic replicator. As you see, it's automatically wired up to the particle simulation. Now we need a solver in order for this to work, so let's make the cube into an active rigid body. It doesn't actually need to be an active rigid body, but it's a quick way of adding a solver into the scene. So we don't need this connection here. We do need to connect the dynamic replicator to the solver, and we need to connect our prototype shapes to the dynamic replicator. Now the dynamic replicator is just responsible for communicating between the particle system and the solver. It doesn't actually generate any rendering objects for us. So let's add just a standard replicator into the scene as well. And we can use the same object as the prototype, in this case a small cube, and feed the result of the particle simulation into the replicator. And now when we play the simulation, oh, well, that was unexpected. Ah, yes, we have gravity turned on. Let's turn gravity off and try again. Here we go. Oh, pile up in Cubesville. So we can control the dynamics of the collision by adjusting things like the bounce and friction settings in the dynamic replicator itself. So if we make the bounce a lot higher, we would expect the cubes to rebound rather than just pile up in the middle. There we go, we've got a little bit of a bounce going there. If we reduce the friction as well, there we go. Here is another example of using the dynamic replicator, and I couldn't resist doing a teeny weeny bit of nodal shading as well. So let's have a look at the schematic for this setup. As you can see, it's very similar to the setup we had with the Spock collider. We have a prototype shape, the icosahedron, which is feeding into a replicator for the purposes of rendering, and also into the dynamic replicator for the dynamics. Dynamic replicator is bridging the particle simulation to the dynamics solver. And we also have a plane in the scene to serve as our ground plane. This is a static rigid body, so it's not going anywhere. We can run the simulation to see how it behaves. As we saw before. And we can cache the simulation and look at the individual frames to see what's going on. It's not immediately obvious, but of course you don't have to use the object that you used for the collision for the dynamics simulation as part of the render. We could use a completely different object, and so for example we could render using blob, and now this gives our rendering a completely different character. This video isn't really about nodal shading, but I thought I ought to just show you the very simple nodal shading setup in this scene. I'm taking the shader inputs, particle ID, feeding that into a gradient as the input value, and then in this gradient I'm using that value to map to different colors. So the input value is the particle ID, which is going to go from 0 to 100%, and then the various colors pop out and are applied to the diffuse color of the object. So here we have the gradient setting the diffuse color, and this gradient here is this gradient here. I think a full account of nodal shading will have to wait for another video. So I think that just about wraps things up. The last word I think we should leave to Spock.